which is the analysis. We have covered the first three sections in the previous video. The first section was graphs of basic functions, in which we studied about some basic functions and their properties, the concept of continuity, and the concept of symmetry. And we looked at the graphs of some basic functions, the straight line, the squaring function, the parabola, the cubing function, the square root function, and the absolute value function. And we studied, when we take the symmetry into consideration, what kind of transformations can be done, how can it be reflected, and things like that in the first section. Then we looked at the horizontal and vertical shifts of a graph, how the equation is modified, and while discussing that, I also was pointing out in the videos once in a while how the domain and ranges are changing. Okay, when we shift a function, its location in the plane changes, right? So the domain and range may change. And then in the next section, 2.3, again we discussed about another set of transformations called stretching and shrinking and reflecting. And we discussed a lot of ideas in that, and how that, again, changes the domain and range, and how to get the new equation, what is the impact of vertically stretching, what is the impact of horizontally stretching, and there is logic behind how the new equation is obtained in each case, right? I remember particularly spending some time on the horizontal stretching part. Okay, now we are going to do, okay, the reason I reviewed this is we are going to do a number of combined problems where we use all those ideas to answer the questions. Okay, so let me begin here. Let the domain of f of x be -1, 2, so that interval, and the range be the interval 0 to 3. Find the domain and range of each of the following. Okay, so the question is asking you to find the domain and range, but in the answer, the guided answer that I have created, first I want to write the translation or stretching or whatever, those kind of, if you try to first focus on what kind of action has been taken on the graph, what has been modified, that will help you decide the change in the domain and range as well. Okay, so here the new function is f of x minus 2. So the input has been modified, so there is a horizontal action, right? And we remember in horizontal, subtracting will actually take you to the right. Okay, so the translation here is right shift 2 units. Okay, as a result, the new domain you see here, that's your old domain. You shift it 2 units to the right. The -1 will go to 1 and the 2 will go to 4. Think about that. Add 2 to both of them. The interval from -1 to 2 goes to the interval from 1 to 4. Okay, shift it to the right. Just because we are doing the first one, so I want to be very clear here. So let me show that. -1 is here, 0, 1, 2, right? So when you shift, 2 units to the right, from -1, 2 units to the right, you go to 1, right? And the other endpoint is 2, 2 units to the right, you go to 4. So your new interval is from 1 to 4. You can see that. Okay, 3 here, 4 here. Okay, and what about the range? and you'd notice that we did not modify the output. It's f of, the f of x is still the same. So the range has not changed, which will still be 0 to 3. The graph has only been shifted horizontally, so no change in the vertical values, right? No change in the range. Next. Now two actions have been taken. One is x minus 3 and the other is plus 1. They are on different objects, right? The x minus 3 acts horizontally on the input. The plus 1 is on the output. Okay, so let me write that here. This action, the first one is on x. This second action is on y. Okay, that might look confusing. Let me write separately. The x minus 3 is on x. The plus 1 is on y. The f of x minus 3 is the y value, right? The function value. That's the y value. So plus 1 on the y value. Okay, so in terms of translations, 3 units, right? And 1 unit up, plus 1. So your domain, okay, the old domain, let me write that here, the old domain is minus 1 to 2. So your new domain is going to be 3 units to the right. Go ahead and write your answer and check with me. That will be your new domain. Okay. The old range was 0 to 3, 1 unit up. So you can write the new range. So it will be from 1 to 4. Okay. In these problems, we will write the equations. Now, you might, if you have just watched the previous video right before this, you might be wondering, have we not already done this? Okay. My answer would be yes and no. We have done these kind of writing the equation from the graph before, but in this exercise now we are combining the operations. Okay. So sometimes it might only be a shift or only a stretch, but sometimes it will be both. It has been shifted as well as stretched, or sometimes even reflected. So let us practice that. Now, the moment you see the shape, please recollect the basic graph. That is my request every time when you see a graph, try to recollect and go back to what was the basic graph. If you don't recollect, pause the video, turn your notes back few pages, go to the basic graphs. Okay. And you will find that this is the absolute value function. Okay, not this, the parent graph. Let me write that here. The parent graph is the absolute value function written like that. Draw that graph. I'm struggling to place it exactly on the origin. This one, okay. And then on this side, like that. And you can see what is happening here. The shape has not only been shifted, but you can see it has also been changed, right? Looks like my graph is more narrower, okay. Now, if you wonder how do I know it's narrower? Let me actually move the one that I have annotated, right? If you bring it back, you see it's the same shape, V shape, but it's more wide now, right? It's wider than the original graph. I mean, sorry, the original one is wider. The given graph, okay, the given graph here, the parent function is wider. The given function is more narrower, right? So there has been some stretching or shrinking as well. In fact, I can say it is vertically stretched horizontally shrunk, right? Okay, let me place it back. There, your equation is, now let's look at the shifts first. Okay, I'll try to write the new equation given graph. Okay, let's say y equals, now it has been shifted 1 unit left, 3 units down. So at this point, you should be able to write this comfortably. Okay, but that's not enough, right? What about the stretching? To understand that, let us look at the, there are two ways of doing it. Okay, I'll show you both. To find, because it has been stressed, I know there has been some factor here. Let me put a question mark here. Okay, so I'll put a question mark here, and I need to know that, like, because it has been vertically, you can see that, when I placed it at the same with the same vertex, I could see that it has been vertically, horizontally shrunk, vertically stretched. So if it is vertically stretched, this function, the output has been multiplied by something, but by what number? To answer that, two methods. I'll call it method 1. Okay, and this is calculation wise a simple method. In this method, you are simply going to take any, let's say, one point here on the graph, and its equation is -3, sorry, its coordinates are -3 comma 1, right? Plug that in the equation. So let's say it was this unknown quantity coefficient, call it some number a. So your equation now will be y is 1 here equals a times x is -3 plus 1 -3. Okay, so what is unknown? Give it a name a. We already have x and y, so don't use x again. Use some other letter, and then take one of the points on the graph and plug it in the equation. It should satisfy, right? Because the whole graph has the same equation. And then you can solve it. Now 1 equals -3 plus 1 is -2. And you have, by the way, that, okay, let me write the left side again. That -3, you can bring it to the left side and write +3. Okay, 1 plus 3 equals a times absolute value of -2. So 4 equals absolute value of -2 is 2, right? Absolute value means always the positive value. So if you divide by 2 on both sides, now you get a equals 2. Okay, so your equation finally, okay, I would say, I'm going to erase this now. In the video you can watch it, the progress, and going to write that. So the equation is 2 times absolute value of x plus 1 minus 3. Okay. Method 2 is not something that you will write. It is just inspection. Okay, and I'm going to explain, what is the inspection. The inspection is this. In the original graph, you move 1 unit to the right, you go 1 unit up, right? That is 1:1 kind of scale there. But in the new graph, if you go 1 unit to the right, you are going 2 units up, right? 2. So the scaling factor, the stretching factor, the vertical stretching factor is 2. For the same amount of horizontal shift, it's 1 in the parent graph, it's 2 in the given graph. Okay, so the stretching factor is 2. That is the inspection. So either way, you can determine that the coefficient should be 2 there. All right. I wanted to go the first one in detail, we'll do little faster in the second and third and fourth. Okay. This is a straight line. You might wonder, why are we even doing this? We know how to write the equation of a straight line, and I'm going to actually do that in case you have forgotten. Okay. And then we will use the concept we have studied and say that we can get the same equation in the new, like by using this method of shifts and translations and stretchings. Okay. So as a straight line, you can notice that the y-intercept is 1, and if you look at the slope, if you just want to count the slope, look at some standard points. Let's say I take this point and the black point. The coordinate of that point is -3, 3. Okay. And if you just look at the rise and the run, this is 2 units, this is 3 units, but going left, so call it -3. Going up, so call it +2. So the run is -3, rise is 2. And based on that, you can write now the slope is 2 divided by -3, which is -2/3. And the y-intercept B is 1, 0, 1, right? The y-intercept is 1. So your equation is y equals mx plus b. That is y equals -2/3x plus 1. Okay, that is the equation. Now let us see if I can get that equation by stretching the parent graph. Okay. Now, in the current understanding, we take a parent graph and we, stretch it, move it. So the question here is, what is the parent graph? If I have a straight line like that, I can go with a very simple straight line as my parent graph. This would be my parent graph. Okay. And what is that? That's the line which, goes through the origin and makes 45-degree angle, exactly at 1, 1, 2, 2, 3, 3. In this case, -1, -1, -2, -2. Sorry, -1, -1, -2, -2, -3, 3, and so on the left, and similarly on the right. Okay. And the equation of that graph is y equals -x. Right? The -1 slope. Okay. Compare that violet line. Okay, although I have drawn a line segment, it represents a line. Compare that violet line with the blue line. It's shifted 1 unit up, right? So the new line. Okay, actually let me even change the color. The new line is in blue color, right? Okay. If you look at the new line, it's y equals -x plus 1, right? 1 unit up. But you see that it is not just shifted up. Some kind of transformation has taken place because they are not parallel, right? If it was still just -x, they would have been parallel. So what has happened? Let us look at the change, and that is where the concept of the slope, similar to the slope, will come into picture. In the parent graph, you go from anywhere, okay? If you go 1 unit left, you go 1 unit up. If you go 2 units left, you would go 2 units up, right? That's in the parent graph. In the new graph, I'll try to, if you go, similarly, if you go 3 units left, you go 3 units up, But in the new graph, if you go 3 units left, you go only 2 units up. So that tells you the scaling factor is 2 over 3. Okay, like that you can write. Or you can also think about it like I said before. You say the equation, you don't know what the coefficient is, call the coefficient minus some kx. Okay, because I know it's not the same parallel line, it has been moved up and also stretched in some sense. Okay, like keeping the horizontal thing same, if you modify only the vertical values, that is some kind of stretching, right? But what is it? I don't know, so I just call it kx for now. There was a minus sign already, so I leave it there, minus kx plus 1. Then take any one point in the graph and plug in, like the minus 3 comma 3. Okay, so that will give you 3 equals minus k times minus 3 plus 1, right? And subtract 1 on the left side. 3 minus 1, 2 equals minus k times minus 3 is 3k. So that gives you k equals 2 over 3, right? So you get y equals from here you get y equals minus kx plus 1, so minus 2 over 3x plus 1, right? Think about this. In the meantime, let me change the color of this particular component. Okay. Y equals minus kx plus 1 becomes y equals minus 2 over 3kx plus 1. Okay. One more. I would now want you to do it, before I do it. Okay, so the parent graph, now we have already studied the reflection also. You can start with the parent graph being the original parabola whose equation is y equals x square. Now what are the successive steps that have been taken here? Let's say first you decided to reflect it, right? Because this is facing down. You reflect on the x-axis, your equation is y equals minus x square. Okay, so call it step number 1. In step number 2, you have shifted it. Now your new vertex is at 2 comma 1. Please, I have said write your own equation and only then check with me. Okay, because you have shifted to the right and up, it will be minus of x minus 2 whole square plus 1, right? Now that's not enough because this graph appears to be, we'll see. Okay, does it appear to be stretched or not? We'll check that. That may not be enough. I should not say that is not enough. That may not be enough. Let us look at the parent graph. With origin there, it will be at 1 1, and then at 2 it will go to 4, right? At 0 it is 0. So that's our original parabola. Now, okay, that looks more like a V. Let me make it more rounded. Okay, that is the parabola. Compared to that, is this graph stretched? Let us check. And I notice, which color? Let me use the red color. That from here, I move 1 unit and 1 unit. Right? I'm just looking at the magnitude of it, not the direction. Okay, it is facing down. That has already been taken care with the minus sign. But as far as the magnitude is concerned, if you go 1 unit, if you move 1 unit on the horizontal line, you are moving 1 unit on the vertical line, which is exactly you did in the original, in the parent graph as well. Okay. If you go 2 units from the vertex in the parent graph, oh, no. I marked that incorrectly earlier. Okay. I need to remark this. At 2, you are at 4, not at 3. Okay, that is why it is looking wider. Okay, in the parent graph, if you go 2 units to the right, you go 4 units up, right? In the new graph, if you go 2 units, you are still going 4 units. 1, 2, 3, 4. Count that. So there is no stretching here, and that's my answer. Okay, that is how you can determine. Sometimes, just by looking at it visually. Okay, let us do this. This one looks stretched. Okay. So the easy part, please go ahead and write, up to whichever step you are able to make progress. The parent, again, the parent graph is y equals x square, which would have been, let us mark it actually for our benefit, which would have been here. Okay. And then it has been shifted right 2 units and down 3 units. So y equals, and no reflection this time. Okay, x minus 2 whole square minus 3. But then you notice when you go 1 unit right, you're going 2 units up. Okay, if you go 2 units right, you have to go somewhere, I think one more line further than that, somewhere here. So how many units is that? That's a lot. Okay. All right. So it's not clear what exactly is the factor here, the factor here. So what I'm going to do is I'm going to say let, y equals k times x minus 2 whole square minus 3. So now you can see in the two methods I was talking about earlier, method 1, method 2. Method 2 was by inspection. By inspection is possible here also, but you may not be confident in that. Okay. The first method which I showed, where you let k and then find the value of k, works all the time. Okay, because that just relies on the hard data. Like you take the actual points, you plug in and verify it, so it will always work. It's at the inspection you might miss something. Okay. Let me plug in here. Take any one point. You can take any point. That's the beauty of it. Okay. Take any one point on the graph. This is 3 minus 1, right? And that should satisfy the equation here. So you should get minus 1 equals k times 3 minus 2 is 1 square minus 3. And that gives you minus 3. If you add here, you get 2, plus minus 3 plus 1, 2 equals k. And okay, so we have the value of k is 2. So therefore, you can say, your equation is 2 times x minus 2 whole square minus 3. Okay. So by inspection, if you go 1 unit right, you are going 2 units up. That was fine. So if you go 2 units right, you should go 8 units up. Now, if you think about it, it makes sense. Okay, this is 4 here, so the 5 is here. From minus 3 to 5. Particularly if you see, you go from minus 3 to 5, which is 8 units. That is 2 times 4 units. What happens 4 units in the parent graph? You go 4 unit up when you go 2 unit right. In the new given graph, you have to go 8 units up, which is 2 times. So that makes sense now. Okay. But you can see, doing it by the method 1 is convenient for calculations point of view. Okay. There is homework problems down there. You can see. Let me write some more. Okay. Go ahead and write. I'm going to start with the parent graph. The absolute value. Step 1, it has been reflected down. So minus of absolute value. Step 2, it has been shifted. So I'm going to look at the coordinate. This is -1, 4. 1 unit left. 4 units up. Okay. Step 3, the stretching factor, right? What I'm going to do, I'm going to say let y equals minus k times x plus 1 plus 4 be the equation. Plus 1 plus 4. And use the point, substitute, I would write here, okay? Substitute that point -1, 4, which is the vertex. You get 4 equals minus k times x is -1. So -1 plus 1, 0. Oh, that doesn't give the value of k. Sorry. I just learned something. If you use the vertex, it doesn't work, okay? You have to take some other point. This is -2, 1. So don't substitute that. I'm going to keep it here. I'm not going to erase it. That's the lesson. Okay, it doesn't work because k times 0 is not going to help you. Take some other point, -2, 1. And you get 1 equals minus k times x is -2 plus 1 plus 4. Okay. Now you solve it. 1 equals the magnitude -2 plus 1 would be 1 plus 4. So you get k equals 3. Okay, k is 3. That means your equation, finally I'll write here, will be y equals -3 x plus 1 plus 4. Okay. I have just 1 minute left in this video, so I'm going to do one more. Pause the video, do it, and then check with me. The parent graph is here. Okay. So you should recognize the parent graph. This is a cubing function. And the equation of the parent graph is y equals x cube. And notice what has been done here. The one that is facing down, the part that is facing down is facing up now. And the part that was facing up is facing down, right? So your new equation, step 1 is y equals minus x cube. It is that it has been reflected. Then step 2, it is moved up, minus x cube plus 1. Okay. Now that's not enough because it might have been stretched. You have to check that. No, it has not been stretched. So that's going to be the answer. How do I know it has not been stretched? It goes 1 unit for 1 unit, which is what happens in the old graph also. Okay. If you go 1 unit left or right, you are going 1 unit right. That is the same thing in the parent graph. So that's the equation. Okay, I'll pause here. I'll see you in the next video.